Hi everybody. This is going to be a lesson about writing electron configurations and drawing orbital diagrams for every element on the periodic table. We'll also learn how to look at the configuration and tell the number of valence electrons. And for the really long configurations, we'll learn how to write what's called a noble gas abbreviation. Basically, the electron configuration is the answers to that Schrodinger wave equation. It's a configuration. It's going to show us what level and sublevel each electron is in within the element's, energy levels, electron cloud, and how many electrons are in each level and sublevel. Now, when we follow when we write an electron configuration, we have to follow what's called, the off-ball principle. Okay, the off-ball principle says basically the electrons are going to occupy the lowest available energy orbital possible, which means put the electrons as close to the nucleus as you can. Like we fill in level 1 before we move on and fill in level 2. And I think you knew that from previous science courses. You maybe just didn't know that it had a name that was called the off-ball principle. Okay. Now, each energy level contains sublevels. This is really important. The number of sublevels in a level is equal to the level number. For example, level 1, which is the closest to the nucleus, has 1 sublevel. Level 2 has 2 sublevels. Level 3 has 3 sublevels. Makes sense, right? Now the sublevels, which are represented by quantum numbers in the Schrodinger equation, for a configuration, we're going to represent them with letters. The letters that we use to represent the sublevels are S, P, D, and F. Notice that they are lowercase, and we should write them as lowercase number or letters when we're writing a configuration. An S sublevel only has one area where you can find electrons. Remember, an atomic orbital is the area described by the wave equation where you're most likely to find electrons. Each area or orbital can hold 2 electrons, so an S sublevel has a maximum capacity of 2 electrons. It doesn't matter if that S sublevel's on the first energy level or the second or the third, an S sublevel always holds a maximum of 2 electrons. A P sublevel has 3 orbitals, which means it can hold 6 electrons. A D sublevel has 5 orbitals, which means that it can hold 10 electrons because each orbital can hold 2 electrons. And an F sublevel has 7 orbitals, so it can hold a total of 14 electrons. Now, when we write the electron configuration, okay, we have to know what are the levels and sublevels that are available to us, okay, to fill in. So we're going to make a little list here, okay, and you should make a similar list, okay. I'm going to make it off to the side and then use it to write these configurations. We know that level 1 has 1 sublevel and it's called S, okay. Level 2 has 2 sublevels. It has an S and it has a P. Level 3 has 3 sublevels. It has an S, a P, and a D. Level 4 has 4 sublevels. There's a 4S, a 4P, a 4D, and there's a 4F. Level 5 has 5 sublevels. There's a P, a D, there's an S, a P, a D, and an F. There is a 5th sublevel that exists in the Schrodinger equation, but we never use it, so it doesn't have a name. So we could just say like ... here, but it's not named. Level 6 has 6 sublevels. And again, there's 2 more that exist in the Schrodinger equation, but we never use them. So we're not going to give them a name. And level 7 has 7 sublevels. We won't even use all of these, so we certainly don't need to name any more. Now, the off-ball principle says that you fill it in from the closest to the nucleus moving out, okay? So here's how you write an electron configuration. You figure out how many electrons are in that atom. For example, lithium has 3 electrons. I know that by looking at the periodic table. So lithium, we start with level 1, S sublevel, and the S sublevel can hold 2 electrons. So this first number right here, this is the level, okay? The letter is the sublevel. Too close to the top. Hold on. Make it too close to the top. It won't let me write that. So let me move down just a little bit. The S, that is the sublevel, okay? And the 2, this is the number of electrons in that sublevel. So this is basically saying level 1, S sublevel has 2 electrons in it. Now that's the max, remember, for an S sublevel. You can only have 2 at the max. Now level 2, whoops, I wanted to stick with the blue color, sorry. Level 2 also has an S sublevel. It can hold a maximum of 2, but remember lithium only has 3 electrons total, so I only need to put a 1 in there. The 2 electrons that are in the 1s and the 1 electron in the 2s, that's my total number of electrons in lithium. And you don't say 1s squared, you say 1s2, 2s1. This is right here the electron configuration for lithium. Okay, now I'm going to erase some of that stuff so I can clean this up a little bit. And the configuration would look like 1s2, 2s1. And we do write a 1. We don't just write 2s. We do write a 1. Some things I want you to notice. It's all written together. There's no space in between. Do you see that? It's all written together. The number of electrons is a superscript, okay? And you could put more electrons in the 2s, but you don't need to because you only have 3 in lithium. So carbon has 6 electrons. So you'd start out 1s2, 2s can hold 2. After the 2s is full, we're going to go over to the 2p, 2p. 2p can hold up to 6 electrons, but we only need 6 total. So we have 2, 4, we need 2 more. That's the arrangement of electrons in a carbon atom. 1s2, 2s2, 2p2. Sulfur has 16 electrons. So you get going and you just count until your little superscripts add up to 16. P, we can fill it into 6. After the 2p, there is no more sublevels in level 2, so we move to level 3. At this point, we're up to 2, 4, plus 6 is 10, and 12. We need 4 more to get up to 16. So we go to the 3p, and it has 4 electrons. Now, one of the things you're going to learn about is called the valence electrons. The valence electrons are the electrons that are in the outermost level. See here, level 2, which is the outermost level, has 1 electron. Lithium has 1 valence electron. Carbon, level 2, is the outermost level. It has a total of 4 valence electrons. In sulfur, the outermost level is level 3. You add them up, it has 6 valence electrons. And you see how the pattern goes. Okay. Now, it would be wonderful if we could fill in the 1s, the 2s, the 3s, the 4s, the 5s, and, just keep counting. Do you remember how when you get out to like level 3 and 4, remember when we were doing the previous PowerPoint, how the levels start getting really close together? And what happens when they break apart into sublevels, the S sublevel is always the closest to the nucleus, and the F sublevel is always the furthest away. And they actually start to overlap each other. Like the 4S is closer to the nucleus than the 3D. And the 5S is closer than the 4D or the 4F, and so on. So what are you going to do then as far as like kind of knowing the exact order? There's 2 different ways. I mean, you can write a chart like this, and you can draw diagonal lines. The diagonal lines give you the exact filling order from the nucleus out. Like it's 1S, and this is the exact order from the nucleus out. 2S, 2P, 3S, 3P, 4S, 3D, 4P, 5S, 4D, 5P, 6S, and etc. The other thing you can do is you can look at the periodic table. And the periodic table can actually guide you as well. So let's write the configuration for potassium, and then we'll do copper, and we'll compare these to the periodic table. So potassium's configuration, potassium has 19 electrons. So it's 1s2, 2s2, 2p6, 3s2, 3p6. Now if you add up all the little superscripts, 4 and 6 is 10, 12 and 6 is 18. After the 3p is full, the next thing you do you see where the arrow goes? It doesn't go to the 3D, it goes to the 4s. 4s1. Now one thing I want you to notice here, do you see that the lithium ended in 2s1 and the potassium ends in 4s1 and also has 1 valence electron? So we could do that by following those diagonal arrows, or if you look at the periodic table, we can number our rows on the table. 1, 2, 3, 4, 5, 6, 7. The row stands for the outermost energy level. Like, take a look at this, okay? Do you see this? The lithium ended in 2s1 and the potassium ended in 4s1. They're both in this little area of the periodic table that is 2 blocks wide. This area right here, this is the S block. All of these elements in the first column end with S1. Lithium ended with 2s1. Potassium ended with 4s1. I bet you could figure out what cesium will end with. 6s1. All of these elements will end with S2. If you wrote the configuration for strontium, it would end with 5s2. That is the S block. The helium ends with 1s2. You see how the helium would fit into that empty space over there. Okay, let's look back at some of the other ones. Look at the carbon. It ends with 2p2. So So I'm going to switch colors here. We'll go with the green. Do you see how this block right here is 6 wide? 1, 2, 3, 4, 5, 6. And carbon is in the second one. Carbon is in, going across, look, row 2, second one over, 2, P2. Did you see that? Oops. If I wrote the configuration for oxygen, I'm not sure why I'm getting that. Hold on. If I wrote the configuration for oxygen, it's in the second row in the P1, 2, 3, 4 position. It would end with 2P4. Do you see sulfur right below it? Do you see the sulfur right there? It's in the third row in the P4 position. Look back at our previous slide. 3P4. Third row, P4. See, this is the P block. And the P block and the S block, those are the two blocks that always make up the valence shell. And they correspond to what row. And you can count, like, for example, if I write the configuration for iodine, it's in row 5, fifth one over. It's going to end with 5P5. So we've got the S block and the P block. Now, what about this element copper? So if we go to write copper's configuration, we'd have, 1s2, 2s2, 2p6, 3s2. Oh, copper has 29 electrons. So we got to keep going until our little superscripts add to 29. 3p6. After 3p comes 4s2. So we got 2, 4, 6 is 10, 11, 12, 18, 19, 20. And then we need 9 more. After the 4s, we would go back here to the 3d. D can hold 10. We don't have to fill it though. We will end with 3d9. Now, if I'm to do the valence electrons here, 4 is the outermost energy level, and there are 2 valence electrons. Do you see that the D is 1 behind the valence shell? And if you look at the periodic table, this center section where the, I don't want to get like another color yet. Hold on, let's do blue. This center section where the copper was located, this center section, this is the D block. Now the D block, okay, is 1 behind the row or the valence shell number. You see that? Like we start with the 4s2, and then it's 3d 1, 2, 3, 4, 5, 6, 7, 8, 9. Copper ended with 3d9. Zinc would end with 3d10. What comes after zinc? We're in the P block, fourth row, 4p1. Let's look back. After the 3Ds, where do we go? 4Ps. Next, you would fill in the 4Ps going right across here. Ps. So I should have used green. Fill in the 4Ps. After the 4Ps, where do you go? Down here. 5s2. Right in here. Where do you go after 5s2? 4d. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Where do you go after 4d10? After you're at 4d10, you go to 5p and then 6s. So here's the 4d right across here, 4d10. Then you got the 5p6s going right across here, fifth row. After xenon, you come down here to Cesium, 6s1, 6s2, but look where the next element goes. Barium is number 56, I believe. It's a little hard for me to see on here. And then you drop down to lanthanum, number 57. Now you look back there, what comes after 6s? It's the 4f. You see that? This area of the periodic table down here, we'll do that in orange. This area right here, this is the F block. All of these elements have configurations that end with F. But this is going to be 2 behind the row number, because we already did the 6s2 and now we're in the 4f, 1, 2, 3, 4, etc., all the way over to 14. And if you follow along after the 4f, you go back to 5d, 1 through 10. Then it's 6p, 1 through 6. Then it's 7s, 1 and 2. And looking back, what's after 7s? 5f. And then you would go to the 5f's, 1, 2, 3, all the way over to 14. And what comes after 5f? Following your numbers, you go back here to RF. And in this area, whoops, I don't want to do either of those things. Oh my goodness. I accidentally, well, we're going to ignore that. It won't let me write. And I got rid of all of them. Okay. So let's review that. I need to, okay. So let's review that. Okay. These are the S's. These are the P's. These are the D's. And we were where the 7, 1, 2, 3, 4, 5, 6, 7. This would be the 7s2. After 7s, we drop down to, remember, the 5f's. So this is the F block, the 4f's and the 5f's. We go the whole way across here. And what's after 5f? After 5f, we have, look back here. Oh, yeah, that's gone. But after 5f, we have the 6. Oh, my goodness, going across here again. The 6t's. Avoided it that time. So you can either use those diagonals or you can just follow the periodic table. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6. Then you got the 5s, 5s2, 4d10, 5p6, 6s2, 4f14, 5d10, 6p6, 7s2, 5f14, then back to the 6d's and the 7p's. And you have the ability to write the electron configuration for any element. So if you look where tin is located, let's see, tin is right there. It's in the P block, it's the second one over, and it's in the 5th row. When we're done writing its configuration, it should end with 5p2. So we start filling them in. We got, ooh, that's too light. I don't want that color. We have 1s2, 2s2, 2p6. And I'm going to go back. Look, we've done the 1s2, the 2s2, and the 2p6. What's next? 3s2, 3p6. 3s2, 3p6. After the 3p6, what's next? 4s2, 3d10, 4p6. 4s2, 3d10, 4p6. Now I think it's wise at this point to stop and count. We've got 2 plus 2 is 4, plus 6 we're up to 10, 12, 18, 20, 36. So right here I'm up to 36. I need to get to 50 though. So I need 14 more spots for electrons. So I filled up to 4p6. So what's next? 5s2. After that, 4d10. That gives me 12 more, but I needed 14 more. 5p2, and I end right where I should. So after the 4p6, there was 5s2, 4d10, and 5p2. You can easily count the number of valence electrons. Level 5 is the highest level number. Count the electrons. There's 2 here, 2 here. 4 valence electrons. If you look back at the previous configurations we wrote, carbon had 4 valence electrons, so does tin. Remember, lithium had 1 and potassium had 1. Elements that are in the same column are going to have the same number of valence electrons. Now the other one I have over there, fermium. You see fermium, number 100? This is the 5Fs, and it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 over. Fermium should end with 5F12. And all your little superscripts should add up to 100. So you can try that one and see how you do. Valence electrons, outermost energy level. Not necessarily the last thing written in the configuration, but the highest level number. You're never going to have more than 8. Why not? Well, you look back. Every time you fill the S's and the P's before you start the D's, you start a new energy level. The S's and the P's are the only ones that are ever going to count as part of the valence shell. Okay, so you have 2 in the S, you have 6 in the P. The B and the F are never part of the valence shell. What's the total? 2 and 6 equals 8, and they call that a stable octet. This is the reason the noble gases are totally unreactive. They already have 8 valence electrons in their outer shell. You're going to see in the future units that we study, the whole reason that elements undergo chemical reactions is that they are trying to get 8 electrons in the outer shell. Noble gases already have 8, so they have no reason to share, gain, or lose electrons and react. So how do you write the noble gas abbreviation? Okay, so for calcium, calcium has 20 electrons. So where's the last noble gas before calcium? Okay, so here's calcium. These are the noble gases. Okay, and the noble gases, they end with, remember the helium ends with 1s2, but the rest of them end with p6. Neon's in the second row, it's going to end with 2p6. Argon ends with 3p6. Krypton ends with 4p6. Xenon 5p6. Radon 6p6. Nothing comes after OG, so we don't have to worry, but it would end with 7p6. The last noble gas before calcium is argon, and it ends with 3p6. So what you do is instead of writing all that 1s2, 2s2, 2p6, what you do is you just say argon. That accounts for the first 18 electrons, and it ends with 3p6. What comes after 3p6? 4s2. By using the noble gas configuration, you can still see the valence electrons and see that calcium has 2 valence electrons. Let's try some others. You got to do silver and radium. Okay. Let's see where the silver is. Right here. Last noble gas before silver, krypton. Krypton has, so let's see. I'm going the wrong way. Silver has what? I'm having trouble seeing the little numbers. Silver has 47. Okay, silver is atomic number 47, and the krypton is 36. So silver, we need 47 electrons. So you've got krypton. That accounts for 36 electrons up to and including 4p6. You need to add 11 more, starting with after 4p6. 5s2, 4d9. 11 electrons plus these 36, because remember krypton is 36 electrons, that gives you a total of 47. You look back over here. This is row 5. Oops. This is row 5. 5s2, 4d, and it's the 9th one over. And it corresponds. Try the radium for a second. Try the radium. Now, if you can't find radium, it's right there. I don't want to switch colors. It's right there. Last noble gas before radium is radon. Radon ends with, do you see that? Radon ends with 6p6. And it's number 86. Radium is number 88. We only need 2 more electrons. What comes after 6p6? 7s2 right there. 7s2. Because radium has 88. Yep. You can still see the valence electrons in both of these. They both happen to have 2 valence electrons. So you'll get some practice at writing regular configurations like this, and you'll get some practice at noble gas abbreviations. A lot of times people ask me, can I use other elements to abbreviate? Nope, just the noble gases. Why the noble gases? Recognize that when you fill in the noble gas, the very next electron starts a new row. You are completing a valence shell and then starting a new row. And that's the only reason you can use the noble gases to do the abbreviating. Now, orbital diagrams. Okay, a box represents the orbital and an arrow represents the electrons. Now, for this, you got to go back to one of those earlier. S has 1 orbital. Do you remember that? P has 3 orbitals. D has 5 orbitals. And an F sublevel has 7 orbitals. You got to know that piece of information. And each orbital can hold 2 electrons. So you can put 2 arrows in each box. Okay. Now, here's my configuration for carbon. So what you do, you have 1s, draw a single box because an S has one orbital, and you put two electrons in it, one up and one down, because they spin in opposite directions. Then you have the 2s. It also is holding two electrons. And then you have the 2p. A p sublevel has three orbitals, so I got to draw three boxes. And look, I only get to put two arrows in three boxes. So the question might be, what do I do? Do I pair them up? Do I do first and third, second and third? Do they point up? Do they point down? Well, there are some rules about that. There's the Pauli exclusion principle, only two electrons in a box, but they have to have opposite spins. We already did that and showed that in these first two. Then there's something called Hund's rule. Each orbital in a sublevel has to have one electron before any pairs are made. That takes care of what to do back here, because each orbital within the sublevel has to have one. I cannot pair those two electrons up. And what this does is it not only shows us that carbon has 4 valence electrons, but now we know how they're arranged. We know there's a pair and there's two unpaired. And that's going to be important when we get to bonding, because unpaired electrons try to pair up with unpaired electrons from neighboring atoms, and they share and they form bonds. So it's important to know not only that there are 4 valence electrons, but how are they arranged? One pair and two singles. Okay? And apply the Pauli exclusion principle and Hund's rule when you're drawing them. So let's do, for example, the sulfur. So it's 1s2. We had this earlier. Oh. So we've got the 1s. S's are always one box, two electrons. Okay. Got the 2s, one box, two electrons. 2p, gotta have three boxes. This one has 6, so it's single, 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 and then I pair them up. We have 3s, pair of electrons. Then we have the 3p. 3 boxes, 4 electrons. Remember Hund's rule, 1 in each. Then you can make a pair. Okay? And this is not, see, that's the edge of the box. So look at the edge of the box. Okay? And now we see how the electrons are arranged in the outer shell, 2 pairs and 2 singles. That's going to be important. So try chromium. Chromium has 24 electrons. Write its configuration and then draw the boxes. So I'm going to start working on the configuration. I just need some space. So I've got 10, 20, I need 4 more. So that's what the configuration looks like. I won't give you orbital diagrams for anything too huge. Run out of room on a test paper. So there's the 1s, 2s, 2p. Since it's a p, I got to draw 3 boxes. 6 electrons, so they're all paired up. 3s, There's a pair, 3p. There's 3 boxes. 1, 2, 3, 4, 5, 6. Okay. And gosh, I know this is tough because it's a little messy drawing it on here. It's a lot better when I draw it on a piece of paper. Hard to write on these screens. So there's the box for the 4s. There's 2 electrons, and now 3D. How many boxes do I draw? 5. 1, 2, 3, 4, 5. And I've only got 4 electrons. I cannot make any pairs because Hund's rule says 1 electron in each before any pairs are made. So I actually have 4 single electrons and then an empty orbital. The valence electrons, right here. We can see that we have a single pair of electrons in the valence shell. So what you learned in this, PowerPoint was how to basically write the configuration like this, how it corresponds to spots on the periodic table, the S's, the D's, the P's, and the F's. How to write a noble gas abbreviation. That sure shortens things up for these long ones. Look at this radium one. That's a lot shorter. And how to draw an orbital diagram. I'm not going to give you anything long like silver or radium to draw a diagram. And on a test or a quiz, if it asks for the complete electron configuration, you got to give the whole thing like this. That's the electron configuration. If it asks for the noble gas abbreviation, then you can do this. If it asks for the orbital diagram, then you need something like this. And in all of them, you're able to pick out how many valence electrons are in the configuration. So you can write a configuration, see how many valence electrons. You could do it as a noble gas abbreviation or with the boxes and the arrows. You'll get lots of practice on worksheets and on WebAssign. Good luck, and see me if you need a little bit of help.